Have you ever picked up a metal spoon that was sitting in a hot cup of tea and burns your fingers? Now think about this. The sun is about 150 million kilometers away from us. There's no air, no water, nothing between us and it. Yet every single morning, that enormous ball of fire warms your skin. How can heat jump across 150 million kilometers of empty space? How does a metal spoon heat up in seconds while a wooden spoon stays cool? And why does standing next to a fan feel so refreshing? The answer lies in the three fundamental ways heat moves through our universe: conduction, convection, and radiation. Stay with me. By the end of this video, you'll understand the exact science behind these phenomena, the mathematical laws that govern them, and you'll never look at a warm cup of tea the same way again. Welcome to Academic Engineering. Today, we're diving deep into heat transfer, one of the most fundamental topics in engineering and physics. Heat transfer simply means the movement of thermal energy from a hotter region to a cooler one, and nature has exactly three ways of doing this. First, conduction, heat moving through direct physical contact, particle to particle. Second, convection, heat carried away by a moving fluid like air or water. Third, radiation, heat traveling as electromagnetic waves, no material needed at all. Let's explore each one, understand the physics, and break down the governing equations in a way that actually makes sense. Imagine you're holding one end of a long iron rod and the other end is placed directly in a fire. Within seconds, you feel the heat creeping towards your hand. That's conduction. Scientifically, conduction is the transfer of energy from more energetic particles to less energetic ones, simply because they're in contact and interacting with each other. Think of it like a crowd at a concert. If the people at the front start jumping, their energy ripples backward through the crowd. The atoms in a heated material do exactly the same thing. They vibrate faster, bump into their neighbors, and pass that energy along. And here's a critical point. Different materials conduct heat differently. Metals are excellent conductors. That's why a metal spoon heats up instantly. Wood and plastic are poor conductors. That's why cookware handles are made of them. This property has a name: thermal conductivity. Now let's put numbers to this. The man who quantified heat conduction was the brilliant French mathematician Joseph Fourier, and his law is one of the most elegant equations in all of engineering. Q equals K times A times T1 minus T2 over delta X. Let's break each piece down intuitively. Q, this is the rate of heat transfer, measured in watts or joules per second. It tells us how much heat energy is flowing every second. More Q means more heat moving. K, this is the thermal conductivity of the material, measured in W per meter times K. Think of K as the material's willingness to pass heat. Copper has a very high K, heat races through it. Foam insulation has a very low K, heat barely trickles through. A, this is the cross-sectional area, the size of the surface through which heat flows. Imagine a pipe carrying water. A wider pipe carries more water. Similarly, a larger area carries more heat. T1 and T2, these are the temperatures of the hot surface and the cold surface. The bigger the temperature difference, the stronger the driving force pushing heat across. And delta X, this is the thickness of the material. A thick wall resists heat flow more than a thin one. That's why thermal insulation in buildings is made thick, to slow down heat transfer. So Fourier's law tells us something beautiful. If you want more heat to flow, use a highly conductive material, make it thin, increase the area, and crank up the temperature difference. Engineers use this every single day, designing heat sinks, walls, pipes, and engines. Now let's put this equation into practice. In this problem, we'll apply Fourier's law to calculate the rate of heat transfer through a material step by step. Let us read the problem carefully. The roof of an electrically heated home is 6 meters long, 8 meters wide, and 0.25 meters thick, and it is made of a flat layer of concrete whose thermal conductivity is 0.8 watts per meter degree Celsius. The temperatures on the inner and the outer surfaces of the roof, measured on one night, are 15 degrees Celsius on the inside and 4 degrees Celsius on the outside for a period of 10 hours. And the question asks us, determine the rate of heat loss through the roof that night. Now, let us move on to the solution. From the problem, we identify the following given values. The length of the roof, L, is 6 meters. The width, W, is 8 meters. The thickness of the concrete slab, delta X, is 0.25 meters. The thermal conductivity of concrete, K, is 0.8 watts per meter degree Celsius. The inner surface temperature, T1, is 15 degrees Celsius, and the outer surface temperature, T2, is 4 degrees Celsius, and the time duration, T, is 10 hours. Step 1. We first calculate the surface area of the roof through which heat is being conducted. The area equals length multiplied by width. Substituting the values, 6 multiplied by 8 gives us an area of 48 square meters. In the calculations column, we note that the temperature difference, delta T, is 15 minus 4, which equals 11 degrees Celsius, and the roof area is confirmed as 48 square meters. Step 2. We now apply Fourier's law of heat conduction. Fourier's law states that the rate of heat transfer, Q dot, equals the thermal conductivity K multiplied by the area A multiplied by the temperature gradient, that is, delta T divided by delta X. Substituting our known values, K equals 0.8, A equals 48, delta T equals 11, and delta X equals 0.25. The temperature gradient, 11 divided by 0.25, equals 44 degrees Celsius per meter, and the full product becomes 0.8 times 48 times 44. This gives us a rate of heat loss of 1,690 watts, or 1.69 kilowatts. Note that the precise computed value is 1,689.6 watts, which we round to 1690 watts. Therefore, the rate of heat loss through the concrete roof night is 1,690 watts, or 1.69 kilowatts. While conduction transfers heat through direct contact in solids, there's another powerful mechanism that comes into play the moment a fluid, a liquid or a gas, is involved. That mechanism is convection. Picture a hot cup of tea sitting on your desk. The surface of the tea is hot. Air molecules right above the surface absorb some of that heat, warm up, become lighter, and rise. Cooler air rushes in to replace them. This cycle of movement continuously carries heat away from the tea surface. That's convection in action. Convection is a combination of two things. Conduction, heat moves from the hot surface into the nearby fluid particles, and fluid motion. Those particles carry the heat away as they move. Here's the key insight. The faster the fluid moves, the more heat it carries away. Blow on a hot spoonful of soup. The faster air carries heat away, cooling your soup much quicker. This is exactly why a breeze feels cooler than still air, even if both are at the same temperature. Convection comes in two types. Natural convection happens when fluid moves on its own due to temperature-driven density differences, like hot air rising from a radiator. Forced convection happens when something external, a fan, a pump, the wind, forces the fluid to move. Forced convection is typically much more powerful. The governing equation for convection is known as Newton's law of cooling, and it looks like this. Q equals H times A times T sub S minus T infinity. Let's decode it. Q, same as before, this is the rate of heat transfer in watts, how much heat is moving per second. H, this is the convective heat transfer coefficient, measured in W over m squared times K. This is a crucial number. It captures how effective the fluid is at carrying heat away. Still air might have an H of 5. Forced airflow could push H to 100. Boiling water can reach thousands. Engineers work hard to maximize H in cooling systems. A is the surface area in contact with the fluid. A larger surface area means more heat exchange. That's why heat sinks on computer chips have fins. They dramatically increase the surface area exposed to air. T sub S is the surface temperature of the solid object. The hotter the surface, the more heat it wants to shed. T sub infinity is the temperature of the surrounding fluid, far from the surface. The bigger the gap between T sub S and T sub infinity, the harder heat is driven away from the surface. Think about a car engine. Engineers design cooling systems with the exact goal of maximizing H and A while keeping T sub infinity as low as possible, all so the engine doesn't overheat. Every variable in this equation matters. Now let's put this equation into practice. In this example, we'll apply Newton's law of cooling or heating to calculate the rate of heat transfer through a material, step by step. Let us read through the problem statement. A 2-meter-long, 0.3 centimeter diameter electrical wire extends across a room at 15 degrees Celsius, as shown in the figure. Heat is generated in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 152 degrees Celsius in steady operation. Also, the voltage drop and electric current through the wire are measured to be 60 volts and 1.5 amperes, respectively. Disregarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. The question asks us to find the convection heat transfer coefficient, H, expressed in watts per square meter per Kelvin. Let us now solve this step by step. The length of the wire, L, is 2 meters. The diameter, d, is 0.003 meters, which is the same as 0.3 centimeters. The ambient air temperature, T infinity, is 15 degrees Celsius. The surface temperature of the wire, Ts, is 152 degrees Celsius. The voltage drop across the wire, V, is 60 volts, and the electric current, I, is 1.5 amperes. We also note our assumptions. First, radiation heat transfer is negligible. Second, the system is operating under steady-state conditions. Step 1. We determine the rate of heat generated in the wire electrically. Under steady-state conditions, all the electrical energy generated is dissipated as heat. The rate of heat generation equals voltage multiplied by current. Substituting, 60 volts multiplied by 1.5 amperes gives us a heat generation rate of 90 watts. The calculations column confirms 60 times 1.5 equals 90 watts. Step 2. We calculate the outer surface area of the wire. The surface area of a cylinder equals pi times the diameter times the length. Substituting, pi times 0.003 meters times 2 meters gives us a surface area of 0.01885 square meters. The calculations column confirms this value as 0.01885 square meters. Step 3. We now apply Newton's law of cooling. Newton's law of cooling relates the convection heat transfer rate to the heat transfer coefficient, H, the surface area, and the temperature difference between the surface and the surrounding fluid. Rearranging for H, the coefficient we want to find, H equals Q dot divided by AS multiplied by the quantity Ts minus T infinity. The temperature difference, delta T, is 152 minus 15, which equals 137 degrees Celsius. So H equals 90 divided by 0.01885 multiplied by 137. Substituting all values into the formula, 90 in the numerator, and the product of 0.01885 and 137 in the denominator. This gives us a convection heat transfer coefficient of 34.9 watts per square meter per Kelvin. And the final result is highlighted in the calculations column. H equals 34.9 watts per square meter Kelvin. Therefore, the convection heat transfer coefficient between the outer surface of the wire and the surrounding air is 34.9 watts per square meter Kelvin. Now we come to perhaps the most fascinating mode of heat transfer, radiation. And this one is in a completely different league. Conduction needs physical contact. Convection needs a fluid. Radiation needs absolutely nothing. It travels through a perfect vacuum. Thermal radiation is energy emitted by matter in the form of electromagnetic waves, or photons, as a result of changes in the electronic configurations of atoms and molecules. Basically, whenever an object has any temperature above absolute zero, its atoms are in motion, and that motion causes them to emit electromagnetic radiation. Here's what makes radiation extraordinary. It travels at the speed of light, 300 million meters per second, and in a vacuum it suffers zero attenuation. That's exactly how the energy from the sun, 150 million kilometers away, reaches us here on Earth. No material needed, no medium, just pure electromagnetic energy streaming through space. Every single object emits thermal radiation. Your body, a campfire, a light bulb, even an ice cube. The hotter the object, the more intense the radiation. This leads us to a key concept. In physics, we use an idealized concept called a black body to understand radiation at its maximum. A black body is a perfect emitter. It absorbs all radiation that hits it and emits the maximum possible amount of radiation at any given temperature. Real objects emit less radiation than a black body, but a black body gives us the theoretical ceiling, the best-case scenario, and studying it gives us one of the most powerful laws in thermodynamics. Think of a black body like a perfect thermal radiator. The hotter it gets, the more intensely it radiates, and the relationship isn't linear. It's far more dramatic than that. The exact relationship between temperature and radiated energy is captured by the Stefan-Boltzmann Law. Q equals sigma times A times T to the fourth, where sigma equals 5.67 times 10 to the negative eighth watts per meter squared times Kelvin to the fourth. Let's look at each variable. Q, the radiated heat energy, in watts. This is how much thermal radiation the object is emitting every second. Sigma, pronounced sigma, this is the Stefan-Boltzmann constant. Its value is 5.67 times 10 to the negative eighth watts per meter squared times Kelvin to the fourth. It's a fundamental constant of nature, just like the speed of light or gravitational constant. A, the surface area of the emitting object in square meters. A larger surface radiates more energy. Simple. T, the absolute temperature of the surface measured in Kelvin, and here's where things get dramatic. Notice that T is raised to the power of 4. This is the most important detail in the entire equation. Let's think about what that means. If you double the temperature of an object, say from 300 K to 600 K, the energy radiated doesn't double. It increases by 2 to the power of 4. That's a factor of 16. 16 times more radiation from just doubling the temperature. This is why the sun, with a surface temperature of about 5,778 Kelvin, radiates an almost incomprehensible amount of energy, enough to power all life on Earth from 150 million kilometers away. This T to the fourth relationship is also why engineers treat high-temperature systems with extreme respect. In jet engines, furnaces, and nuclear reactors, even a modest temperature rise causes a massive increase in radiated thermal energy. Accounting for it isn't optional, it's critical. Let's bring it all together. Conduction is heat transfer through direct contact and particle interaction. It follows Fourier's law. Q equals K times A times T1 minus T2 over delta X. The key player is thermal conductivity, K, how freely a material allows heat to pass through it. Convection is heat transfer between a solid surface and a moving fluid. It follows Newton's law of cooling. Q equals H times A times Ts minus T infinity. The convective coefficient H tells us how aggressively the fluid strips heat from the surface. Faster flow means bigger H means faster cooling. Radiation is heat transfer through electromagnetic waves, no medium needed. A black body emits the maximum possible radiation, governed by the Stefan-Boltzmann Law. Q equals sigma times A times T to the fourth. Temperature raised to the fourth power means small temperature changes have enormous effects. In the real world, all three mechanisms usually act together. A running engine loses heat through conduction into its metal parts, convection to the coolant, and radiation from its hot surfaces simultaneously. An engineer who understands all three can design systems that are safer, more efficient, and more powerful. From the spoon in your morning tea to the rocket engines that carry humans into orbit, heat transfer is happening everywhere, every second, governed by the same elegant laws we just explored. Fourier gave us the key to understanding solids. Newton gave us the law of convection. Stefan and Boltzmann revealed the power hidden in temperature. Together, these laws form the backbone of thermal engineering. Now, here's something to think about. Every electronic device you own, your phone, your laptop, your gaming console, has engineers who spent months solving heat transfer problems to keep it from melting. The next time your phone feels warm in your hand, you'll know exactly why. If you found this valuable, hit the like button and subscribe to Academic Engineering for more in-depth engineering breakdowns. Drop a comment below. Tell me which mode of heat transfer surprised you the most. We'll see you in the next one.